revise before I start what we were telling. Suppose this is my Cm versus Cl. I'm flying here, let's say 1, I have to fly at 2. I want to know how much elevator I should deflect so that I can again trim at Cl2. So relationship between delta E required, sometimes we say delta E trim, and Cl trim is what is a control problem for this flight mechanics, whatever we are discussing. How do I formulate it? Let us see. We know Cl should be equal to Cl alpha into alpha plus Cl delta E into delta E. For simplicity, I have put Cl not equal to 0. You can introduce Cl naught here and do the derivation, and most likely I will be giving you that in assignment. Then Cm will be Cm naught plus Cm alpha into alpha plus Cm delta E into delta E. You are clear? Because here we have seen Cl is function of alpha and delta E. We are not talking about any dynamic condition. So since Cm has come because of Cl, so Cm also will be function of alpha and delta E. So Cl I have expanded in a linear way, Cl alpha into alpha plus Cl delta E into delta E. Similarly, I can write Cm alpha into alpha, Cm delta into delta E. But Cm naught we cannot neglect because Cm naught is a very stringent condition to ensure that airplane has a positive angle of attack trim, that is Cm naught should be greater than 0. Now, think once it has come to an equilibrium, what will be the value of Cm? At trim, what happens? At trim, Cm will be equal to 0, right? And the Cl will be equal to Cl trim. Whatever I am looking for, maybe I am looking for this, so that time Cl equal to Cl trim at 2, and Cm has to be 0, otherwise it will not be trim. If I now do this, introduce these things here, what happens? Let us see that. If I introduce this, then I get Cl trim equal to Cl alpha into, now alpha becomes alpha trim, Cl delta E into delta E, let's say trim word I am using, which I physically mean that it is a delta E required. What will happen to this equation? Since it is at trim, so Cm has to be 0. So 0 equal to Cm naught plus Cm alpha into alpha trim plus Cm delta E into delta E trim. What is our aim? Let's not get lost in all this equation. What is our aim? We want to find out what is the relationship between delta E trim and Cl trim, so that I can often know if I want to trim at this particular Cl trim, what is the delta E trim or delta E required, right? So to do this algebraic adjustments, what we will do is, I will write the step. I can write alpha trim is equal to Cl trim minus Cl delta E into delta E trim divided by Cl alpha. Isn't it, from this equation? I can write this alpha trim equal to Cl trim minus Cl delta E into delta E trim divided by Cl alpha. Now this alpha trim expression I will be plugging into this equation. That is Cm naught plus Cm alpha into alpha trim. Instead of alpha trim, I will put this expression, Cm delta E into delta E trim. Now you could see that alpha trim is vanished, so delta E trim and Cl trim will remain in this. So if you do this manipulation, I leave it to you to derive this small relationship. I repeat again, I will be putting alpha trim here in this expression, and then try to find out relationship between delta E trim and Cl trim. So we are eliminating alpha trim from using these two equations, and then you will get some term like, which I am sure you will be able to do it. And write the final expression and that will be delta E equal to minus Cm naught by Cm delta E minus Cm alpha by Cm delta E into Cl alpha minus Cm alpha into Cl delta E into Cl prime. Let me check. Minus Cm naught by Cm delta E minus Cm alpha by Cm. So I can write this delta E equal to delta E naught plus d delta E by d Cl trim into Cl trim, where d delta E by d Cl trim is nothing but minus Cm alpha by Cm delta E Cl alpha minus Cm alpha Cl delta E. Right? What I have done? This whole, what is delta E naught from this expression? Very simple, Cm naught by Cm delta E. So I have put a neat diagram, I have developed, or I am presenting a neat expression where delta E equal to delta E naught plus d delta E by d Cl trim into Cl trim. What is the meaning of this? This I call again trim because this is required. If I know delta E naught value, how do I know? I need to know Cm naught, which I know. I need to know Cm delta E, I know. So I know delta E naught. I need to know d delta E by d Cl trim. It's a Cm alpha I know, airplane. Cm delta E I know. Cl alpha I know. Cl delta E I know. So this term also I know. Okay. So whatever Cl trim I want, I put it here. These numbers are fixed for low speed. So I can get what is the delta E trim required. Is this clear? That was our purpose. I want to know what for a given Cl trim how much delta E I should deflect. Or it is, again, if I take you back to that discussion, I was flying here. If I want to fly here, this will give a negative pitching moment. So I need to generate a positive pitching moment by putting the elevator up. How much elevator up? That will be decided by what is the Cl trim here and what are these values. So I know how much elevator up I have to do. As simple as that. Okay? So that is why I say this is a control solution for elevator, and you call elevator control. Okay, now we'll go a little more insight into it so that we get a little better insight of what are you doing. We'll do some approximation. We'll now go a little bit of discussion for this term. What is this d delta E by d Cl trim? This is given by minus Cm alpha by Cm delta E Cl alpha minus Cm alpha into Cl delta E. Typically, Cl alpha value will be around 5, between 5 and 6. Cm delta will be around 1. Cm alpha would be around -1. This is also -1. Cl delta is little less, 0.5, 0.7. So I can do a simple approximation for this specific purpose. I say this gentleman, right, this term is less compared to the first term. So I can write d delta E by d Cl trim approximately equal to minus Cm alpha by Cm delta E into Cl alpha. So what does it tell you? So what we are getting an expression is d delta E by d Cl trim is equal to minus Cm alpha by Cl alpha into Cm delta E. Now, could you see Cm alpha by Cl alpha is what? Cm alpha by Cl alpha is dCm by d alpha divided by dCl by d alpha. If everything is linear, it is dCm by dCl. So I can write here this is equal to minus dCm by dCl by Cm delta E. So this is d delta E by d CL trim. How do I add value to this for a designer's, from designer's perspective? See here, one thing I know that if Cm delta is very high, very large, this value will go down in absolute sense. What is dCm by dCl? Remember, we have derived dCm by dCl as minus static margin, right? Which is nothing but minus xnp fixed, neutral point fixed, minus xcg bar, so divided by Cm delta E. Okay, so now you could see that if static margin is high, then d delta E by dCl trim will be what? If xnp and xcg are constant, then d delta E by dCl trim will become 0. It's a neutral stability point. But if this stability margin is large and large, then d delta E by dCl trim also will increase. That means you need larger delta E to change the same CL trim from one point to another point. This gradient will be too high. So pilot will have a lot of difficulty to trim from one aircraft trim to another aircraft trim. So this gives you a connection, the handling qualities for the pilot through static margin. Okay, this is one understanding. Second one, once I write delta E equal to delta E naught plus d delta E by dCl trim into CL trim, I am knowing that for CL trim, for this CL trim, this is delta E record, this CL trim, this delta E record, like this, you know. So pilot will develop a feel from that delta E, how much delta he requires to give for a CL trim, or he thinks in terms of, he gets a feel in terms of speed. So you are giving delta E and speed, that sort of mapping you are doing for the pilot. Okay, this is one way of developing a feel for pilot, but that's not a very good way of developing a feel. That is why in a reversible control aircraft, we try to give the feel through the stick force. That is where some little, we will talk about stick free stability. Just I stop here, but please remember, you can give a pilot feel through delta E, CL trim or V trim combination, that if you are at this speed, put that much of delta E. So he develops a feel, okay? However, another way of giving a feel for reversible control is that give through the stick force gradient or through stick force, right? Which we'll be talking sometime later. So, after doing all this thing, what is our learning? So many expressions we have written. So what is the learning? Let us just summarize in a few minutes. As I have been telling you, once for all, you should do this derivation, a very straightforward derivation. However, you should understand what is their real importance in terms of designer, how you're going to use it. Say there's a cruise flight, okay? What CL you will be flying at a cruise? Say, if you say I want to cruise for thrust required minimum, that means you know that I have to fly such that CL equal to CD naught by K, right? This is already you know in performance. So there is a particular CL, okay? Suppose you are flying the machine at some CL which was not for thrust required minimum. Now you find for thrust required minimum, I have to fly at a CL here, let's say. So that means at a higher speed, but CL is given by CD naught by K. So immediately you see that this relationship delta E equal to delta E naught plus d delta E by d CL trim and into CL trim will tell you if you want to fly at this CL trim, how much delta E required. That comes from here. Okay? Similarly, if you want to go for a climb, you need a particular CL. So how much delta E to have that CL? Again, this expression will tell you. Clear? So that is the importance of this term. Okay, I will be solving problem based on this, which will make things much clear to you. But as I have told you that I will have a Mann Ki Baat session where we will be taking up some problems also, so that your understanding is not only clear, it is crystal clear. Okay? We have been talking about stability and control of an airplane, and by now you must be tired. We have written so many expressions. In my opinion, at this juncture, we should try to solve some problem which are directly relevant to designing of an airplane. Once we solve those problems, you will get better feel for this, whatever expressions we have written, whatever equations we have derived. So what will be my approach is, we will start from the beginning, what we have been talking about, and at an appropriate time, we will try to solve a numerical, right? Like this, we will create a workspace for you where you can yourself work for a problem, and you know how to apply whatever we have been talking so far in a real design scenario, okay? So we'll go a little slow, because I could understand that writing so many expressions blackboard, and sometime you will forget that we are talking about an airplane. Many times I used to get a feel that I am doing some sort of a mathematical or numerical course where I need to know how to differentiate, how to find maxima, how to find minima. So it's the right time that we should come back and try to see what we have done and how can you use this for a real aircraft. Let us go back. What is our primary aim? Our aim is to design an airplane which should have a takeoff, climb, say takeoff, then climb, cruise, maybe loiter, landing, and there could be maneuver as well, right? Let us see here. When I am trying to climb, what is happening? If I again go back a little bit, if this is the airplane, okay, and it is going like this. This is, you know, by now, this is flight path angle. And if I am talking about the steady climb, then I know that if this is CL, this is CD, this is the weight, and somewhere there will be thrust. What I know for a steady climb and unaccelerated climb, that is, it will follow a rectilinear motion. The center of gravity will follow this flight velocity, assuming that angle of attack is very small. Most important thing is center of gravity will follow the rectilinear path, and that is possible only when you could see that if this is CL, I mean it has a lift, I can multiply by. Similarly for drag, I can write drag, which is half rho v square into CD. So for your completion, I write drag equal to half rho v square s CD, and lift equal to, you know, half rho v square s CL. Coming back to the steady climb, when this airplane is going like this, what is expected, what I should maintain? I should maintain that if I write it here L for you, otherwise you get confused. See, L should be able to balance W cos gamma, right? So L should be equal to W cos gamma. What does it tell you? If I now switch over from climb to cruise, in cruise, I know L should be equal to half rho v square SCL, and that should be equal to W. So what is the difference in climb and in cruise from trimming the airplane point of view, what is the difference? You know that from here, if I say CL, CL will be W cos gamma by half rho V square S, and here the CL will be equal to W by half rho V square S. So which CL is more? Definitely cos gamma, gamma is some positive number if it is climbing. So this CL climb is less than CL cruise. So what is the implication of this? In performance we have seen it means the induced drag CDI, which is K CL square, that means induced drag CDI for a climb is less than CDI for a cruise. That is a drag coefficient. Okay? CDI for a climb is less than CDI for a cruise. This is from my performance perspective. No issue, right? But from stability and control point of view, what does it mean? From stability and point of view, you could see that the CL required to trim for a climb is less than the CL required to trim at cruise. What is the implication in terms of control? Let us understand this. Then we take you back to this graph, CM versus CL or alpha, whatever you are comfortable. And this is the CL and this is the trim point, right? Or the equilibrium point, trim. So for a climb, it is CL, I see C, this is for climb. And for cruise, I write CL, CR. So if I am trimming the airplane for a cruise, and if this is the point CL cruise, then for climb, I have to have a CL which should be less than CL cruise. Is it clear? Because CL climb, if I write CLC, CLC is nothing but W by half rho V square S into cos gamma, and we have seen CLC is less than CL cruise. So if I am trying to climb at CLC, you could see that if I had to trim the airplane, and if it's the CM versus CL graph, if I try to trim the airplane at CL cruise, it will automatically generate a positive pitching moment because this is statically stable. But we want to trim the airplane here, that is, I want this graph to look like this. So what I have to do, I have to nullify this positive moment. So how can I nullify this positive moment? We know it can be done through elevator. This is the elevator. Now, how much elevator to be deflected? That will depend upon how much positive moment has to be nullified by generating a negative moment. So how do you produce negative moment using elevator? If this is the tail plane, what you have to do? Negative moment means you have to put the elevator down. As you put the elevator down, there is additional delta CL, and which will about a CG will give you negative moment. So this delta E, whatever you have deflected, should be sufficient enough to generate a negative moment whose magnitude will be equal to this much a positive moment. So that is the control problem. Okay, this is clear? Now the question is, how do I know what is that elevator required? And we know that. For that we have devised a relationship which is delta E naught plus D delta E by DCL into CL trim. So if I want to know what is the delta E required for climb, I should replace. So I write delta E during climb will be equal to delta E naught plus D delta E by DCL into CL climb, CLC. If I want to know how much delta E is required for a cruise, so I will write delta E required for cruise will be equal to delta E naught plus d delta E by dCl into Cl cruise. That will tell you how much delta E is required. This part is clear? Okay. Now next question may come, what is delta E naught, what is delta d by delta Cl, and we have also elaborately explained that. And just for revision, because we will be solving problems soon, so we need to recapitulate whatever we have done before we ensure that we are not lost into equations. So you know delta E equal to delta E naught plus d delta E by dCl into Cl trim, and delta E naught was approximately shown to be minus Cm naught by Cm delta E, and d delta E by dCl was minus dCm by dCl by Cm delta E. I am putting approximation because we have neglected few terms. Okay. So what is the message? For an airplane, delta E naught is known because airplane will have a fixed Cm naught and Cm delta E if it is low speed airplane. If it is a high speed airplane, this value may change with incorporating Mach number effect. Similarly, d delta by dCl, how do I know? This is dCm by dCl. Okay. dCm by dCl is what? It has a direct relationship with static margin. What is static margin? It is the distance between neutral point and CG. Remember dCm by dCl, approximately I can write as xCg minus xn stick fixed. Right? This is stick fixed. Why are you talking about stick fixed? Because it tells you absolute value of delta E required. Right? Okay. So dCm by dCl is known. For a given configuration, xCg will be known and neutral point also will be known. So this is known. Cm delta E and Cm naught are also known. So I actually know these numbers. This number, these are known to us. And we have to just plug in the Cl cruise or Cl, whatever trim you are using. Right? So once this part is clear, I, as a student, would like to know what is Cm naught as a revision and what is Cm delta E before I really become champion of using this expression. So what I will do, we will now go back. What is Cm naught? What do you understand by Cm naught? And what is the meaning of Cm delta E in a little exhaustive manner, because that will help us in solving problems. Please remember, whatever so far I am discussing here, I am not talking about a maneuvering flight. Okay? Correct? For a maneuvering flight, we have seen that you have to put additional elevator deflection, which we will be again revisiting while we are solving a problem. But at this point, for this whatever I am discussing, we are not talking about any maneuvering flight. Okay, now let us see what is the Cm naught and what is the Cm delta E, and allow me to put something like Cl delta E. What are these parameters, or what are these aerodynamic derivatives? For example, what is the meaning of Cm delta E? Let us understand. This is dCm by d delta E, partial derivative. What does it mean? How do I physically generate field for this? You know, at equilibrium, I am talking about steady state. Let's say the airplane is at equilibrium to cruise, right? And you know that lift force will be function of alpha and the delta E, because otherwise lift also will be function of how it is doing pitch rate, right? How the rate of change of angle of attack is changing. But we are considering a case where it's in equilibrium. It is just like having some alpha E and some delta E, some alpha and delta E. Alpha is the angle of attack. So that is how we write Cl also as a function of alpha and delta E. So Cl we wrote as Cl naught plus Cl alpha into alpha plus Cl delta E into delta E. We are exploiting the fact that CL is linear function of alpha and delta E, so that we can write it like this. So here also, if I ask you, we'll ask the question, what is CL alpha? The CL alpha is dCl by d alpha is a partial derivative. What does it mean? It means what is the change in CL per unit change in alpha, keeping other thing constant, right? That is important. Okay, so delta E is also constant, other thing, speed, etc. is constant. So that is the meaning of CL alpha or the partial derivative. Now similarly, what is the meaning of Cm delta E? Let us understand that. Again, this is partial derivatives dCm by d delta E. Okay, what is the physics behind this? Let's say this is the wing, this is the tail, okay, and here is the CG of the airplane. Now if I give a delta E deflection, as you recall, as per the convention, delta E is positive up, no, delta is positive down, sorry. As per the convention, delta E is positive down and delta E negative up. That is, if I am putting the elevator up like this is negative delta E, and if I am putting it down like this, then this is positive delta E. This is a matter of convention. Okay. So now, in order to understand what is Cm delta E, which is a partial derivative, and by definition we understand the change in the Cm, that is the pitching moment coefficient, per unit elevator deflection. So we give first a positive elevator deflection, and let's say this is delta E. So what will happen? It will generate additional lift delta CL, so that will give a moment about CG, and that can be non-dimensionalized, and we can get the value of Cm delta E. But one thing is clear at this point, for a positive delta E, the moment will be negative. So sine of Cm delta E is negative. Okay? And this is also called, if you recall, called elevator control power. Naturally, if Cm delta is strong, so it will have a very command over pitching the airplane, giving nose down or nose up moment. So it is a control power, and it is called elevator control power because this moment is generated by elevator. Okay. So that is the physical meaning of Cm delta E. So Cl delta E also very clear from here, that how much change in Cl because of elevator deflection, right? So these are two terms we should know before we try to solve a problem. Now next we will try to know what is Cm naught. What is Cm naught? This is Cm naught. When I write, it means Cm naught of the aircraft, total aircraft. What is happening, you see? What is in our mind when we talk about Cm naught? We have seen if this is Cm versus Cl, and this is Cl or alpha, whatever suits you. So this part is Cm naught, right? Let's, for simplicity, I assume everything is symmetric. So let me put it versus alpha, right? So what is Cm naught then? Cm naught is Cm at alpha equal to 0. So this Cm naught contribution should come from, the Cm naught contribution should come from, it could come from wing, it could come from fuselage, it could come from tail. There could be other auxiliary surfaces also. But we will be mostly talking about wing contribution and tail contribution, and assume that fuselage contribution to Cm naught is negligible, or there are empirical way to find out, which we will be doing, showing you when you solve some numerical problem. What is the message here? Why do I want a Cm naught positive? We want Cm naught positive because I want to trim the airplane at positive angle of attack. है ना? Okay. If Cm0 was negative, I still can have a trim here, otherwise statically stable, but this is at trim at negative angle of attack. So I don't want to do that. I want to have at positive angle of attack. So that is why we need Cm0. But then Cm0 I should generate automatically from the aircraft by adding up the contribution of wing, fuselage, and tail. Right? So what is the contribution of wing? We have already done. We'll just write an expression to give you better insight into it. Cm0 of aircraft is nothing but Cm0 due to wing plus Cm0 due to fuselage plus Cm0 due to tail, right? We have already done this, and we derived expression Cm0 due to wing. I can write it as Cm AC wing plus x bar into CL0. So we have the Cm0 tail I can write as CL alpha tail into VH neta T into IW minus IT plus epsilon naught. You have already seen this derivation, and we are saying Cm0 fuselage we are neglecting now. Okay. Or we can put some value called Cm0 Fs, right? Which we do not know at this stage how to compute, but we'll solve some numericals to tell you how you can compute that. Let us come back to the very important here. What is Cm AC wing? So we have seen Cm0 wing is Cm AC wing plus x bar into CL0. Let us understand each term here. Please do not forget, what is our aim? Our aim is to ensure that the Cm versus alpha or CL graph, if it is alpha, this is Cm0. I need to have the Cm0 desired. For example, if I need Cm0 equal to 0.02, then Cm0 because of wing, because of fuselage, because of tail should totally give me the value 0.02. Okay, that is important. So now what we are seeing, what is Cm AC wing? Because we are trying to find out what is the contribution of wing towards Cm0 of the whole aircraft, right? So now, you know that we are very clear now that for a cambered aerofoil, Cm AC wing is less than 0, which is negative, typically minus 0.01 to minus 0.1. You will find number like this. Let us see what are these Cm AC wing and x bar CL0. Let us draw a wing. And let's say this is x AC wing bar, and let's say CG is here, CG of the whole aircraft. Please understand. So I give this in nomenclature XCG aircraft. This is for the aircraft. Don't forget this. People generally creates confusion within themselves. So now we know that this cambered aerofoil will have Cm AC wing, which is negative, though by sign convention, this is the conventional sign for positive sign. So what is happening? Cm0 wing, this is about CG actually, right? That will be what? You have to transfer Cm AC wing here, so it is here. And then at alpha equal to 0, you could see that there will be a lift here, which is CL0, the coefficient part. Remember, CL versus alpha, this is CL, this is alpha. For a cambered aerofoil, at alpha equal to 0, there is a CL, which is called CL0. This is CL0. So this CL0 also will give you a nose down moment about CG. Do you see this? So if I write x bar as XCG aircraft bar minus x AC wing, you could see that Cm naught wing about CG is Cm AC wing plus x bar CL naught, and if AC of the wing is aft of CG of the airplane, so this contribution also will give a negative pitching moment. So total Cm naught wing because of camber aerofoil, because of AC of the wing is behind CG of the airplane, this will contribute to negative value. Thank you very much.